All right, everybody, let's begin. Sorry for a little delay there. So, welcome to our first revision lesson. Let's just have a quick chat about our plan for the next week and a half. Well, it's a week really, and then we're finished maths for the term. So, we're week 10, this is where we are today. We're going to go over a summary of the unit, hopefully before recess, and then you guys will have that lesson after recess for revision. Friday's a revision lesson, Tuesday's a revision lesson, and Wednesday our test will be over the recess lesson. So we will begin the test at 10:30. So you don't have to come up here at 10:15, have a bit of a recess, have a breather, and then come up for a test at 10:30. It goes for 80 minutes until 11. All right, so that's our plan. Make sure you're organising with me, catch up with me to do a few tutorials and so forth. Monday, Tuesday lunches are both good times for me. I can't do after school either of those days, but Monday, Tuesday lunch work well, and leading up to it as well. Remember last test we spoke about, the test, basically it's almost 10:30 now, which makes it just over 168 hours away. So every hour between now and then that transpires, you can move towards getting the result you want, or away from it. So every TikTok video you scroll through is an opportunity to be doing more revision instead. All right, so let's start at the front here. We'll talk about what this sheet is. This is a summary of probably what should go on your cheat sheet. So this will be a good opportunity for us to just recap what we went through in the textbook. So we have 3A, and 3A starts with tangents and normals. It's an enormous exercise. There's 16 questions, but basically you're just finding the equation of tangents and normals, and then some of the later questions go on to say where does the tangent intersect the curve again and so forth. So a bit more algebra involved there. So we will read, we've got two ways, well really three processes for finding the equation of a tangent or normal. We've got general form, we've got the formula, and then we've just got an intuitive approach. How do I find the equation of a line? Okay, so that was 3A. Then what I would like to do is lump sort of 3B, 3C, and 3D together. Okay, where we assess it in the test is sort of one question that incorporates all of them together. Because in 3B, we talk about when is a function increasing and decreasing. Well, that's just when the sign diagram of the derivative is positive, increasing, and the sign diagram of the first derivative is negative, decreasing. That's all that's going on with increasing, decreasing. That's some cheese right there, right? So then it's on to 3C, stationary points. Stationary points are when the slope is horizontal. So we're still just looking at the sign diagram of the first derivative and looking at the roots. And we can identify whether it's a maximum, okay, goes from increasing to decreasing, positive slope to negative slope, or a minimum. And we also have stationary inflection that popped up in 3C. Then on to 3D. Now that was broken up into two parts. 3D.1, we learn about points of inflection. They occur when the second derivative equals 0 and the function changes shape. So it changes from concave up to concave down. So points of inflection, and we have two types of points of inflection. So we need to know how to differentiate between the two. And we also talk about intervals for when a function is concave up, concave down. That's in 3D.1. Then in 3D.2, we supplemented the textbook with the graphing questions booklet. Okay, so there will definitely be a graphing question where we give you the graph of a function, and we say, draw a graph of the first derivative, draw a graph of the second derivative, based off the function that we've given you. Okay, so that's that'll pop up today, opportunity to recap that today, and definitely you can expect one of them in the test. So that's taken us all the way to 3D, and that's sort of like couple of weeks ago, all right, and so then the rest of the stuff is relatively fresh. All right, we've done kinematics, all right, so we're using calculus methods to solve equations of motion and so forth, displacement, velocity, and time. In 3F, all you're doing, finding the derivative and using the derivative function to work out what's the rate of change. If y is the function, dy on dx tells you the rate at which y changes. And then yesterday we went through optimization, okay? And again, with the optimization problems, just break it down into its parts. In the later parts of the problem, all you're doing, differentiate the function, draw the sign diagram, and state the optimal solution. Answer the question, right? Okay, and then that summary table at the bottom, that's really important. That's really going to help us out with those questions from 3D.2, those graphing ones. So that's a really, really important table. Okay, so let's have a look at the test summary then. So we got Wednesday, 10th of April, lesson 3 and 4. We'll begin at 10:30. It goes for 80 minutes. We've got 56 marks. Graphics calculator permitted. Sorry, so I was writing this last night, so I've got a few changes to make as we read through it. You know, they say don't drink and derive. So, so bring your graphics calculator. You're allowed a single-sided A4 page of handwritten notes. So that's going to be your cheat sheet. And the formula sheet that we've provided for you on the back of your notes book, you're allowed to bring that as well. Okay, so really your cheat sheet, you have lots of room to put the stuff on that you think is important that's not on the formula sheet. Okay, we've talked about the content there. Here's the skills checklist. I think we've sort of alluded to what's going on there. The only thing I'll draw your attention to is the bottom dot point, that there will be a conjecture problem. Okay, again, break it down. Get the marks at the start. They'll start easy, all right, and they'll get progressively harder. And I think perhaps in successive lessons, we'll see how we go, but we can talk about strategies, like general strategies for conjecture problems, as well as we've gone over about 5 or 6 of them, I think, together. So I'm happy to go over more, but that might be something just hit hard yourself. It's going to be on a tangent or a stationary point. They're the ones we can do it on. We've got the revision resources there, so lots of tests, all printed, so everyone's grabbed them up the back, except these fellas, they can get them shortly. Conjecture question booklet, okay, so you'll use that now, but don't throw it out because there are some questions in there for integration when we get to that later in the year. So the first, I think, 14 or 15 questions are calculus ones. We've got the graphing relationships booklets. Okay, on the second dot point, review sets, all questions are relevant except the only ones we don't need are review set A, question 15, and review set B, question 15. So question 15 from both review sets. These use double angle formulas, which aren't a part of the methods course. So we don't need to do those questions. All right. So if there's no general questions about the test, let's get into this review together. I've got these 5 questions that we're going to go through. My plan would be we'll try our hardest to get them done in the next 20 minutes, which will take us through to recess. Any questions before we begin? All right, so up to you where you record this. You're very welcome to just watch, okay? You're very welcome to write it down as we're going through it, but this has got to be a good summary of all of the skills. So question 1 here is straight from 3A. It says find the equation of the tangent and normal. Let's just do the normal. We don't need to do both, they're very similar. And we've got the function y equals e to the 0.5x at x equals ln4. And we can use any process we want. Maybe we will use we'll just use y, maybe we'll use the formula today. So I've got the formula for the tangent written on the front there. The normal at x equals a. I'll write this out and I'll show you how it relates. Normal at x equals a is y equals minus 1 on f dash of a, x take a plus f of a. Okay, that's the equation of the normal. And we're going to find this in exact form. We're not going to, it says find it in exact form, which means we're not converting anything to decimals. All right, so our tangent is at x equals ln4. And so that means the formula for it is just f dash of ln4 times x take ln4 plus f of ln4. That's all we're doing. All right, so you can see we need the derivative function to put it in there. We need the original function to put it in there, and that's all we're doing. So let's over here, let's just evaluate what is f of ln4. When I put ln4 into the original function, I would have e to the 0.5 ln4. Now we can't simplify that as it is, we need to rearrange it a little bit. So I will just focus on this part, e to the 0.5 ln4. That 0.5 I can move to the top of the 4 here, I can make it the power. So it's e to the ln4 to the 0.5. All right, and 4 to the power of 0.5, that means 4 to the half, which is the same as the square root of 4. So that simplifies really nicely to e to the ln 2. And e to the ln x simplifies to x, so e to the ln 2 will simplify to 2. So this part of our equation is just 2. Okay, next we need f dash of ln 4. So that means we need to find the derivative function. Alright, dy of dx, or f dash of x. It will be 0.5 e to the 0.5x. Alright, now here, okay, if you can see it, we already know when I put ln 4 into e to the 0.5x, it comes out as 2. Alright, we can see that there. When I put ln 4 in, alright, that comes out as 2, which means this part is going to come out as 2. So that means I have 0.5 times 2, which means I have positive 1, sorry. Change it to a negative 1. Good. And so then what we'll have is minus 1 on top of 1. Alright, so minus 1 on top of what's f dash of ln 4? Well, that's just 1, so that's going there. Times x, take ln 4, and then plus 2. And then we just evaluate this. That minus 1 on 1, that's just 1. So we have minus x plus ln 4 plus 2. So the equation of the normal, it's the equation of a line, right? Y equals mx, so the slope is minus 1, mx plus c. This is the y-intercept of the normal, this whole thing here, the constant term left over. Now, be clear, that's not going to be ln 6, it's ln of 4 plus 2. The plus 2 is a separate term. All right, so that's the first one. And maybe I'll just show very quickly on the calculator. We did go through a strategy for graphing the normal. So if I just sketch the original function, which is e to the power of 0.5x, and I just want to look at the original function. Not too bad. We're doing the tangent at x is ln 4. So we can go sketch, normal, and we want the normal at, and then we just type in an x value, ln 4. That's what it is there. And I think we press equals and it gives us the equation. Now it's given us the equation, right? But one flaw with the calculator is it won't give you the equation in exact form. Okay, see there where it says y equals minus x? Well, that tells me I've got the correct minus x here. And then we've got ln 4 plus 2. If you type this into your calculator, guess what it's going to be? 3.3862. Okay, so that's one way that you can verify you are correct, that you have the correct equation of the normal. So I'll just show those calculator skills quickly again. So what I did, we pressed sketch, and we can bring up tangent or normal, and then you type in the x value where you want to draw the tangent or normal. So we wanted the tangent, I just started typing in ln 4, I pressed enter, it draws it, and then I press execute again, and it will tell me the equation of it. Okay, so let's move on. Question 2. So here's a small change I wanted to make. I wanted to make that squared just to make the calculus a little bit more complex when we perform it. All right, consider the function, find f dash of x and draw its sign diagram. Okay, so you'll see this, if you're going over those practice tests, you'll see this question pop up in every single test. We're just giving you a different polynomial, all right, same concepts apply. So if we're going to differentiate this, we basically have two options. We could fully expand it and then use simple differentiation. All right, that'll probably take just as long, really. Or we can use the product rule, u times v. Let's use the product rule. So we've got x to the 3, 3x squared. We've got x take 2 squared. And so we'll be using the chain rule, 2 times x take 2 to the power of 1 multiplied by 1. All right. And f of x, n take 1, f dash of x. Smash it all together. U dash v plus u v dash. Okay, so here's our first derivative, and we want to draw the sign diagram of it. Now, we only get 2 marks here, so I've shown you when we've been going through it how to make a manual argument, but I don't want you to do that. I just want you to refer straight to your calculator. And so what we're going to do here is sketch the original function, which is x to the 3 multiplied by x take 2 squared. Now, here's a hint as well, is later on in this question, you'll be required to graph it. And I've said, when you're required to graph, we're going to give you a Cartesian plane. So that means look ahead, you'll see the Cartesian plane and you'll see the constraints of the Cartesian plane over which you should be looking at this graph. All right, so there's the original function. We won't look at that. We'll go straight to the derivative because we want the sign diagram of the derivative. All right, let's just standard it. All right, and all we're going to do is G-solve those roots and indicate when is it positive, when is it negative. So I've got a root at 0, I've got a root at 1.2, and a root at 2. 0, 1.2, 2. All right, and what we can see, all we're indicating is it above, above, below, above. Okay? All right. That is part B. Sorry, that's part A. Hence, state where the function is increasing and where the function is decreasing. All right, so we've got basically 2 ways we can say it. All right, so I'm going to say increasing when it's positive, right? So you go, okay, x is less than 0, 0 to 1.2, and then x is greater than 2. Okay, so that's an appropriate way to answer it. We're just indicating the intervals where it's positive. Or you could just write that. X is less than 1.2 and x is greater than 2. Both of those are acceptable. All right, then we have decreasing, and it's decreasing when the original function, when the derivative function has negative slope. So this is our f dash of x. Good. Okay. Hence, state the nature and coordinates of stationary points. So, let's stress quickly, stationary points occur when the slope is 0. Okay, that's a stationary point. And we have 2 types of stationary points. We have what's called a turning point, and we have a point of inflection. And then we have 2 types of turning points, right? We have a maximum and we have a minimum. All right, so I've tried to indicate this a couple of ways. We've got Venn diagrams and so forth. So we're familiar with maximums and minimums, and we should be looking at that going, okay, increasing, decreasing, increasing, decreasing. That's a local max. Decreasing, increasing. That's a local min. Okay, so those are both turning points. All right, and then in our notes book, we've got the sign diagram of the derivative. It does this. If it's increasing, goes horizontal, and then keeps increasing. What would that look like? Okay, positive slope, goes horizontal, and then positive slope again. That's where we have our stationary point of inflection. So I should specify that's a stationary POI. So if it asks for stationary points, that's this or this, okay? If it just asks for turning points, then it's only maximum or minimum. Okay, what's our one say here? It says stationary points. So we're answering both. We can see local max at 1.2. And then the y value, local min at x is 2, and then the y value. And we have stationary point of inflection. We can just write stationary inflection. And then we've got x is 0. And when x is 0, the y value is going to be 0 as well, so we can anticipate that one already. And these other ones, I'm just going to get them later when we graph the function. We can have a bit of a look at it then. Okay, so that's part B. But that's part C. Let's move on to part D. We need to find the second derivative. All right. So you could look at this and go, okay, that's going to be a little bit annoying because there's sort of two product rules going on here. We've got U times V, and then over here U times V. But we can expand this one quite easily. All right. That's just going to become 2x to the 4. And that's going to become minus 4x to the 3. All right, so that, when we differentiate that part, we can use simple differentiation, which means we only need to use the product rule here. So, I'll write the function up here, f dash of x, and then we'll differentiate it. We've got 3x squared times x take 2 squared, and then we have plus 2x to the 4 take 4x to the 3. Okay, so those two terms, we'll use simple diff. Here we need to use the product rule. U is 3x squared, U dash is 6x, V dash. All right, smash it together. F double dash of x, U dash V plus U V dash. Right, so that's the derivative of this part, but don't forget we've got to differentiate these terms over here, plus 8x to the 3, take 12x squared. Okay, so that's our second derivative. Draw its sign diagram. All right, straight to our calculator. Let's use our calculator. So we're going to select the derivative function, the second derivative, graphing the second derivative, and we'll g-solve those roots. So we've got 0. And we know that, we already know there's an inflection point at 0, 0.7101 and 1.689. Okay, so on 3 significant figures, this one here will become 0.710. Okay, the 1 rounds down, so that's going to be, and here the 9 rounds up, which means that 8 becomes a 9. Okay, so the first 3 non-zero numbers, all right, write the first 4, round the fourth one. 1, 2, 3, 4, round the fourth one, that's what we get. Very good. Okay, and now we're indicating when's it positive, when's it negative. So we can see to the left of 0, negative, positive, negative, positive. Okay. Hence state intervals when the function is concave up, concave down. Concave up when it's positive. So from 0 to 0.71. Concave and x being larger than 1.69. And then concave down, x is less than 0 when it's negative, 0.71. All right. Now remember, when we're stating intervals, we include the point unless there's an asymptote there. Good. Okay. Hence state the nature and coordinates of any points of inflection. Well, we know we have stationary POI at 0. All right, so that was part, let's try and break it up. This is part E, this is part F. So stationary POI at 0, 0. And then we have non-stationary POI. And then we've got these. All right, now we know this is the sign diagram of the second derivative. And the rule for a point of inflection is that the sign diagram must change sign. Occasionally you have a root on the second derivative that doesn't change sign. That's in like 5% of cases. But we notice here at the root it changes sign. Here at the root it changes sign. And so that means we have non-stationary inflection at 0.71. And and the y value, and another one at 1.69, and then the corresponding y value. All right, so let's go back to the original function. Let's observe all of these features, and because then what we'd be required to do is to graph it. So if I go up to y1, we just graph y1. All right, and I'll zoom in on it a little bit. Let's go from just -2 to 3 and -5 to 5. Okay, so let's see, what can we see? Firstly, let's talk about increasing. It's increasing until we get to 0, and then it's increasing again from 0 to 1.2, okay? I'm going to do a really rough sketch of it here so I can point at it while I'm doing it. Things like this, and goes like this. Okay, so increasing till 0, increasing till 1.2, decreasing till we get to 2, and then increasing again. Next, local max at 1.2, local min at 2, stationary inflection at 0, concave down, concave up. All right, on to the next one. Here's the sine diagram of the second derivative. Concave up from 0 to 0.71, okay? From 0 to 0.71, that's going to be the point of inflection. Concave up, it opens up over that interval. Concave down until we get to here somewhere. What's that value? 1.69. All right, let's fill in all the y values. We can see those features. So first we need when y is 1.2, when x is 1.2, we've got y is 1.10. When x is 2, looks like 0. All right, so go back, make sure we fill them all in and get those points of inflection as well. There's no way to G-solve points of inflection other than knowing the x values and typing in the x values. So 0.71, we have 0.5955, 596, and 1.69, we'll have 0.464. Now, this kind of question here, right, you're really relying on your calculator. There's lots of marks here. These are lots of easy marks to get. I want everyone to get 4 marks in this question, okay? So practice that, make sure you know how to use your calculator, make sure you get it right. And really, that's a good summary of B, C, and D. Okay, so I don't know if we've got time to go to the next one. Maybe we'll have an early minute for recess. And when we come back, we'll finish it off. Any questions so far? Cool, all right. Okay, we're back. So we're continuing on. I think question 3, 4, 5 will go a bit quicker. So on question 3 here, we have a kinematics question. We have the displacement of a footy launched above ground level is given by this equation, launched by Isaac Heaney. 1 plus 15t take 4.9t squared is the displacement. Okay, t is time in seconds. Part A, find the velocity and acceleration functions. All right, just like you expect, we're just going to differentiate, okay? The derivative of displacement is velocity. All right, and if I differentiate this, the 1's going to disappear, we're going to have 15, and we'll have to take 9.8t. All right, 2 times 4.9 will be 9.8. And if we were to draw this sine diagram, remember with kinematics we only consider positive values of time. We can go straight to our calculator and sketch that, or you can calculate it manually. Both will probably be as quick as one another, but it's going to be what, 15 on 9.8, just under 2. I'll calculate that in a moment. And then A of t is the derivative of v, which is the second derivative of displacement. So when we differentiate this, we're just left with minus 9.8, which is the equation of a line. If you graph this, all right, if you graph A of t, here's x, here's y, it's just here. Y equals minus 9.8. It doesn't matter the x value, it's always negative, which means this one's always going to be negative. And has anyone evaluated this yet? Or I'll do it so pretty fixed quickly. All right, I'll show you what I mean. So let's sketch the original function. We'll look at how we can use our calculator here. So we've got 1 plus 15t plus 1 plus 15, and we use x, don't we? And then take 4.9 x squared. All right, so there's the original function. You can see it's a quadratic, it's going up there and then coming back down here. So that's where it's going to hit the ground, which means we have a constraint for which the model is valid for. All right, negative y values don't make sense because it's not going to go below ground level unless it's an absolute missile. So, so that's the original function. Let's sketch the first derivative. And I said it'll be 15 on 9.8, just under 2. And we'll get it to 3 sig figs. We've got 1.5306. Okay, so write the first 4 figures. 0 doesn't round up, it stays as is. So we've got 1.53, and we can see it going from above to below. All right, so all we're asked to do in part A, find the velocity and acceleration functions. That's the velocity function, that's the acceleration function. Draw their sign diagrams, done. And be clear, this is v of t, this is a of t. Okay, that's part A. Part B, when is the speed increasing? All right, so I've got that summarized on 3E here. I'm talking about kinematics. We've got a couple of dot points. The speed of an object is the bottom, this is the bottom dot point, is the magnitude of velocity. If v of t and a of t have the same sign, then speed is increasing. All right, and so they're both negative after t is 1.53. So speed is increasing. To answer part B, speed is increasing after t equals 1.53. And of course, think about the context of this. If you boot a ball into the air, immediately it starts slowing down because gravity's pulling it down. And then as it falls, it's going to speed up, right, until it hits the ground, and it'll hit the ground with the most force. And we can find the time value for which it's valid, but we won't worry about doing that. Speed is increasing after t is 1.53 or t is larger than 1.53. Either of those is absolutely fine. Okay, so that's part B. And then lastly, part C. What is the maximum height and when does it occur? So what we should see is the displacement is maximized here. Okay, this is the first derivative. The first derivative tells us the turning points, the local max and min on the original function. We can see we have a local max when time is 1.53. So max height at t is 1.53, and we want to know, well, how high does the footy go? Well, that's just going to be, what's the displacement when time is 1.53? The displacement is just height above ground level. So when time is 1.53, and we'll just go back to the original function, it's helpful to graph it, use your calculator, okay? And we can g-solve the max. I'm going to need to zoom out because it's been launched. All right, you can only g-solve if you can see it, but we can g-solve that max, or we can type in the x value. But you can see that x value 1.53, that's what we expected, and the height 12.47 meters. 12.47. So 4 figures, 7 rounds, 12.5. Don't forget units. That's seconds. Okay, good. So that's our kinematics question. Let's move on then. We've got a rave. The number of people at a rave is given by the equation n of t equals 10e to the t cos t, where t is time in days after the rave starts. Okay, so we've got a rave, it's going to go for a day and a half. So t is time in days. How many people are at the rave, part 1, initially? Part 2, after 12 hours. All you're doing here is going, okay, n of 0, and then n of 12. No, not 12, okay? It's not time in hours, it's time in days. So 12 hours is how many days? Half a day. 24 hours in a day, so you'll be finding n of 0.5. So there will be those kind of like implicit things to look out for, time in days, time in hours, time in seconds, and so forth. So we're finding n of 0 and n of 0.5, and you can put 0 in here and type that in, or you can do it in your calculator. Type in 0.5. I think the best way to do it is to graph the function, because we are going to be referring to it. So let's type it in. We've got 10 e to the power of x, and then just cos x. All right, that's pretty good. And so really, if you think about it, we're only considering positive values at time. So we could set our x min as 0. All right, it's valid for time being positive. And it doesn't make sense to have negative people at the party, so we won't consider below the x-axis either. So we can see the constraints over which we're interested in. Now we want to know what's the population when time is 0, so how many people initially, and the y value there is 10. 10 people. And then when x is 0.5, we've got 14.46. Now, make sure you read the questions. We will say this. It says, how many people are at the rave? Answer to the nearest integer. Integer just means whole number, okay? So if we have 14.46, the nearest whole number is 14 people at the rave after 12 hours. All right. So that's part A. Part B, find n dash of t. So if this is our function, we're going to differentiate it. We need to use the product rule. We have u times v. All right, here's one function, here's another. So u is 10e to the t, u dash will be the same. V is cos of t, v dash is negative sine of t. Smash them together. Okay, there's n dash t. Determine the rate of change, answer to 3 significant things, initially. So that means we can just go straight back to our calculator here. When time is 0, oh look at that, the rate of change is 10. So this is part A, this is part B, now we're on to part C. C part 1, we've got n dash of 0, so we can put 0 in here, or we can put 0 in the calculator. We've got 10, and then we want n dash of, again, after 12 hours, that's half a day. So when time is 0.5, and I've got the dy on dx, the rate of change is 6.56. Okay. Now we need to give a unit here, don't we? We need to give a unit here. So on the, what's our n? That's the number of people. So we have people per, and then what's our period of time? Days. People per day. All right, here people per day. So when time is 0, there's 10 people coming in per day. When time is 12 hours, half a day, there's 6.56 people coming in per day. All right, that's that one. When is determine the rate of change? Find n dash t. Determine the rate of change done. When is the rate of change maximized? Okay. So the best way to do this is to sketch the derivative function and go, when's the maximum on the rate of change function? When is the rate of change maximized? And if we g-solve the max, it's just after x is 0. All right, so it's very close to x is 0, and we'll just state that as it is there. I'll talk about what that means. So part E, sorry, when is the rate of change maximized? Maximized when t equals, and I'll write out what they've got here, which is 6.055, and then they've got e minus 8, e minus 8, All right, now, you won't get marks if you write that, okay? You'd have to at least write it in scientific notation, which is 6.055 times 10 to the minus 8. That's all it means. That's the only difference. Okay, 6.055 times 10 to the minus 8. And what does that actually mean? But it means 8 zeros. Okay, 1, 2, 3, 4, 5, 6, 7, 8. You put a decimal after the first zero, and then you just write those numbers. 6055. Alright, so that's a recap of scientific notation. But maximise when? We just graphed the derivative function and found it maximised. And that's days. That's when the rate of change is maximised. And that would correspond with a point of inflection on the original function. Okay, determine the exact value of t such that n dash of t equals 0. All right, so here's n dash of t, and we want that to equal 0. So we got 10 e to the t cos of t, take 10 e to the t sine of t equals 0. When is the rate of change equal to 0? Sorry,
we're getting marks if we just write 0 days.
Possibly. The question in the test is like this. I made it up last night, so this is a pretty bad number. Yeah. So because it's 3 significant figures, like if you write, I would give you mark. Yeah. It's only worth 1 mark. So yeah. All right. Let's have a look here. So what are we up to? We're finding when is the rate of change equal to 0. That means it's not increasing, it's not decreasing. It's talking about the local max on the original function. So if we're going to solve this equation, by the way, we're going, all right, I need to factorize something. Okay, I need to try and break it down so I can apply the null factorial. We can see we've got 10 e to the t is common, times cos of t take sine of t. All right, 10 e to the t does not equal 0. Which means we're focused on this component. Cos of t take sine of t equals 0. And we've seen this pop up in the first test, all right, solving this kind of thing. I think the best way to do it is to look at your unit circle and go, when is the cos value equal to the sine value? And there'll be 2 solutions. We'll have when t is pi on 4. All right, explain it in terms of the unit circle, right? Here, at 45 degrees at pi on 4, the x value and the y value are equal. Cos is equal to y. Sine is equal to cos when the angle is pi on 4, and the other one would be here when they're both negative. However, those would be outside the domain. We just need to answer that one. Okay, that's 4. Let's move on to 5 then. All right, consider the function here. We've got the function below has roots at A, B, C, turning points at D and E, stationary inflection at F, and non-stationary inflection at G and H. And we're asked to plot them. All right, so we're given a function and we're told plot those points on this graph. So I'll sketch up here to the best of my ability. Some point of inflection, stationary, another point of inflection there, mid. So let's do something like this. Max. Okay, firstly, sketch the roots. Roots at A, B, and C. Roots are where it crosses the x-axis. All right, so you can plot them on the graph alongside. Turning points at D and E. So turning points are when the function turns, okay? They're local maxes and local mids. So we have here D and E. All right, we have a stationary inflection. All right, so it's stationary, changes from concave up to concave down. That's our stationary inflection. And we have non-stationary inflection at G, okay? Concave down, and H. Concave down, concave up. All right. So the points of inflection are probably the harder ones to identify, but you'll notice they're always occurring between stationary points, aren't they? Stationary point here, stationary point here, stationary point here. I'll look point of inflection in between stationary points. Okay? Determine intervals where the function is increasing. Alright, so this function is increasing until you get to D, and then it's increasing after E. And say increasing, yeah. Alright, so when would you be walking uphill? Over those intervals. That's part B. Part C. When is the slope decreasing at the greatest rate? So this is something I'm really trying to emphasize. When is the derivative function maximized? When is it most negative? So it says when is the slope decreasing at the greatest rate? So that means it has to be over some interval over which we're decreasing. Alright? And let's talk about that table. Let's bring that table back out. Okay? What does this function tell us about f of x? Read that bottom point. Points of inflection on f of x are the turning points on f dash of x. What are turning points but maximum and minimums? This point here is when the slope is steepest. Okay? And so you can see, like if you put your ruler along it, you can see like, oh yeah, it's not very steep, it's not very steep. All of a sudden it's very steep at that point, and then it starts leveling off. Okay? So points of inflection are always going to be where the slope is largest in magnitude. So when is it most negative? When is it decreasing the most? We've got 2 points. We would say G and H. G and H. Points of inflection on f of x correspond with the turning points on f dash of x. That's when it's most negative. All right. And where are we up to? Draw a possible graph of f dash of x. Okay, so this is the graphing relationships. F dash of x. Let's draw the sign diagram of f dash of x. What does it look like? Alright, we can see positive until we get to D. We're increasing until we get to D. Then we're negative until we get to F. And then we're negative again until we get to E. And then we're positive after that. So we can see increasing till we get to D, decreasing till we get to F where it's horizontal, and then decreasing again until we get to E where it starts increasing. So all f dash of x shows you, the only thing you're required to do is go, when is the original function increasing, when is it decreasing? Now, what would this look like on a graph? All right, plot those points, D, F, I'll try and line it up with the axes. So there's our axes there, we've got point D, point F, and point E. All right. It goes from above to below. So at point D, it's above, and then it goes below. It touches at point F, that's a root, okay? It's below, it touches at point F, but then it's still negative. It stays below until point E where it passes back over. Now, let's reconnect this with, the prior question, which was when is the slope decreasing at the greatest rate? Here's the slope function. When is it decreasing at the greatest rate? That means when is the slope most negative? It's most negative here and here. What does that correspond with on the graph? G and H. Okay, the points of inflection on f of x correspond with turning points. All right, so we can list them there because we know that turning points on f dash of x are points of inflection on f of x. Okay, that's the first derivative. Second derivative. Okay, so now all we're doing is going, all right, when is it concave up? When is it concave down? So what we can see is concave down until we get to G. So sign diagram of the second derivative. Concave down, which means negative, until we get to G. Then we're positive, okay? Concave up. Your bowl is opening upwards. So there's your cereal bowl. We'll put some Weet-Bix and milk in it. Between G and F. All right, concave up. And then concave down, okay? Between F and H. Furthermore, right, in this question, we're told where the points of inflection occur. It says it. It says you have points of inflection at, stationary inflection at F, non-stationary inflection at G and H. and then we're concave up after h, the bottom collective numbers. Okay, so then all we're doing is sketching a function with these properties. Alright, so the axis is to the left of g anyway, the y-axis. Alright, so we've got it's negative until we get to g, and then it's positive until we get to f, and then it's negative until we get to h. So I was just going like this. Okay, here's g, here's f, here's h. It's below, above, below, above. Alright, last thing to emphasize. Turning points of inflection on the original function correspond with turning points on the derivative function, which are the roots on this function. Alright, so turning points, there's another one there as well, GFH. Points of inflection, GFH. Turning point, GFH. Roots, GFH. Okay, so there we go. There's an enormous summary of all of the stuff we've gone through. So